Testing. Hey, welcome back. This next lecture is going to be the first of 4 on the topic of hashing. We're going to look at open and closed hashing, which are somewhat similar, not exactly similar, but somewhat in comparison to the third type of hashing we'll look at, which is extendable hashing, which will sort of cover almost as a different data structure because it's really different than the first two in a few significant ways. The idea of hashing takes a similarity from the idea of bit vectors, and that in both cases there's some additional property we need to have on our elements. When we talk about a hash function, we say that we need to have a hash function available on our data, in much the same way a bit vector needed to be enumerable, or the type needed to be enumerable. For a hash function, we need to be able to say that it's possible to hash on our key and get an index, and that index then has to be in the range 0 to size -1, where size is the size of some array. So we have here 0, size -1, and that's the array we're dealing with. So the concept is that we have an array, and the hash function, the job of the hash function, is to take a key as input and produce an index for our array. What we're trying to do here is gain the advantage of speed. Hash tables are going to focus on being fast data structures, and the fastest thing we're able to do as far as insert and such and lookup is we can very quickly insert into and look up in an array if we happen to know the index that our element in the array is at, as opposed to having to search the entire array for what we're looking for. And so if we're able to quickly produce an index of some kind from a key, then that's a beautiful situation. We simply say, well, plug the key in this function and produce an index. I can then go right to that index in the array. And this process of converting a key to an index is known as hashing because it uses the hash function, and that's where the whole data structure gets its name. So the idea, for example, would be, let's say we have the name Sue, the string literal. I'm going to pass in that string literal to my hash function, and let's say the hash function gives me 3 when I plug Sue in. I can put Sue at cell 3 in my array. Now, the idea here would be that this is going to tend to be not some large if-then-else thing inside the hash function. We're typically doing some sort of numerical calculation on whatever it is we're passing in, an integer or the letters of a string or something like that. So we're not planning ahead here for all possible strings. If we somehow knew in advance the possible strings we had, let's say we knew we had 7 particular strings and we had a table of size 7 from 0 to 6, we might be able to then plan some function that said, if it's one particular string, then hash it to 0. If it's the next string, hash it to 1. If it's the third string, hash it to 2. And have some function that used an if-else, large if-else statement to hash each of our 7 strings to a unique spot in that table. Or what we might do instead is say, well, I'm going to know these 7 strings in advance and use some sophisticated math and create a special hash function that will take those 7 strings as data and hash them each to one of those unique cells, 0 to 6. We'll come back to that in just a moment. I can do the same thing, of course, with other values. So if Jim hashes to 5, then Jim goes at cell 5, and that's what we'd be doing down here in this small table as well. If we had only 7 strings, then one of them would hash to 0, one would hash to 1, one would hash to 2, and we could set up a hash function to do that specifically. The problem comes with the fact that we don't necessarily know our strings in advance. And so if I had these 7 strings and I set up either using an if-else, which is going to take longer and longer, the more strings we have, the larger the table is, or if instead I set up some mathematical function that very cleanly and quickly converted each of our 7 strings to a unique one of those cells. Now if suddenly I want to say, well, let me have a 7th or 8th string in my collection, the chances are that if I'm using a mathematical function, it's not going to somehow work out that that 8th string is going to happen to hash to 7. I probably need to start over from scratch and create a new mathematical hash function that would convert all 8 of my strings to the particular hash cell 0 to 7. And so the more cells I have, the harder that will be to do, to create a hash function that hashes each of these values uniquely. And in addition, if I'm going to use a large if-else statement, the more strings I have as possibilities, the longer that if-else statement will be. And so both options for trying to have this perfect hash are unappealing. And as a result, it's very likely that even if we had a perfect, or even if we knew our strings in advance, we'd find it difficult to come up with a function that would hash those 8 strings to the 8 spots in the table very nicely. So we don't really try and do that. We don't tend to try and gear our hash functions towards a particular data set, even if we knew the data in advance. Certainly, in most cases, we don't know the data in advance. And from any given year, we don't know what students are going to be in the university, what their names will be. So there's a number of different possible names people might have, and we're stuck with the particular names that people that are going to school here happen to have. And so the problem we run into then, since it's difficult or impossible in many cases to end up with every string hashing to a unique location, we end up with a situation where we may have 2 strings go to the same location. And that's a problem, because as long as the strings are not going to the same location, if I hash on Sue and get cell 3, I put Sue at cell 3. Later on, every time I want to look for Sue, I hash on Sue again. I will get cell 3 again, because if I keep passing the same input, I keep getting the same output. And I can look up in cell 3 and there's Sue. And same thing with Jim. I hash on Jim, I get cell 5. I jump to cell 5, there's Jim. Later on, I want to look up Jim, or perhaps the information record attached to Jim. I hash on Jim again, get 5 again, jump to cell 5, and there's Jim. But now that I hash on Bob and get 3, well, now we're saying that in the future, if I want to look for Bob, I will hash on Bob, I'll get 3, and I'll be able to find Bob in cell 3. But that's not the case, because Sue is already there. So if I hash on Bob and it tells me put Bob in cell 3, I can't do that because Sue is in the way. And so that's what would motivate the concept of, well, what happened, and what can we design a hash function that uses only the particular strings that we want to use and perfectly maps them across the table indices so we don't have this possibility. Even if we had exactly the same number of possible keys as table cells, it'll still be difficult to create such a hash function. And in general, we don't have only that number of possible keys. We typically have a very large key set from which we've taken a limited number of keys. And that's the example I used was university names. We would have a very large set of possible strings for names from which we happen to have 36,000 names pulled out that are the 36,000 students here at U of I. And so if you have a limited number of table cells and an infinite number of strings, you're guaranteed at least one of these cells will have multiple strings hashed to it, if you have more strings than table cells. And that's called the pigeonhole principle for those of you who have not heard it or don't remember it from a discrete math course like our CS173 or some other discrete math course you may have taken. But that's, it's common sense, but it's a principle given a name. If you have a certain number of boxes and you have more items than boxes, then one of the boxes ends up with more than one item. At least one of the boxes ends up with more than one item. And that's what happens here. So since we have an infinite number of possible strings, it's possible, there's a chance that if we go picking strings at random and saying, well, out of all the possible strings, I'll make a table of size 36,000. And then out of all the possible strings that I could have as names, I'll pick 36,000 of them. And I'll hash on all of those, and I'll happen to get every one of those strings hashes from 0 to size -1, one of those keys. It's certainly possible that would be the case. Just like it's possible you say, well, there's 365 days in a year. Pick 365 people off the street, and there's a chance every one of them has a unique birthday. On the other hand, and what I'm about to say may drop your jaw if you haven't heard it yet, but it's the honest truth, and it can be shown mathematically. It turns out that if I pick 23 people at random, chances are better than half that 2 of them share a birthday. There's 365 days, and yet if I pick 23 people out at random, chances are that instead of being at at 23 different birthdays, chances are better than half that 2 of them will have the same birthday. As odd as that sounds, it's the case. So the idea is when you have this, and assuming birthdays are randomly distributed, there may be certain days that more people are born on than other days, but we expect birthdays to be somewhat, close to randomly distributed. Even then, when we have 23 items out of a possible 365 table cells, even then we're at least 50% chance of getting a collision with two people and their birthdays. And so it's not enough to say, well, I have a table size of 300 or 36,000, and I'll pick 36,000 strings, and my chances are I'll get 1 string for every cell. The table would be only even a quarter full or an eighth full, and we'd already be expecting perhaps at least 1 collision. So there's the whole idea of collisions is that they're likely to occur. Now we're not likely to get huge numbers of collisions. But even in a table that we've inserted relatively small few values into, we will expect to get some collisions, which is what this is called. The idea of 2 of our selected keys hashing to the same spot is called a collision. And so we need to have means of dealing with that. We're talking immediately next about how to pick a hash function that will minimize collisions. But after a while, even with the best possible hash function, you're still likely to get collisions as you start doing more and more insertions. And so we do need to have a strategy for dealing with them. One possible strategy we will use, of course, is to keep the table size larger and larger. Because if we have a few elements inserted into a small table, they're more likely to collide than if we had a few elements inserted into a very large table. But we don't want to make we don't have huge infinite amounts of room in memory either, and no matter how big we make the table, there's still a chance of some collisions. And so we're better off making the table size reasonable, as we'll discuss, and then we'll hash our strings or hash whatever into the table, and we'll get our few collisions that we expect and deal with them in the ways we'll discuss next. So anyway, that's the idea of hashing. The fundamental idea is hash on a key to get an index, go to that index, and there's your value. And the slight glitch in the idea is that we might take 2 strings that we pass in, or 2 keys, and they might hash the same location instead of different locations. And the more keys we insert into a table, the more likely that is to happen. And so we need to have some means of saying, well, wait a minute, if Sue and Bob hash to the same place, what do I do about Bob? Sue is there first, how do I handle Bob? So I've already alluded to this a little bit in the discussion I've already had here, but when we talk about a good hash function, one thing we might talk about first is what makes a bad hash function. And here's an example of a very bad hash function. We've taken the key as input, and we return 6. That's a very bad hash function. We're saying everything hashes to 6. So the first element can insert nicely in cell 6, and the second, third, fourth, fifth, sixth, seventh elements are all going to have collisions. Similar to if I was to, open a bottle of something like ammonia or cologne or some, very strong smelling thing at the top of a lecture hall, right at that top of the lecture hall, the smell is going to be really, really intense because your ammonia or cologne or whatever is all concentrated up there. Over time, it'll sort of waft through the entire lecture hall, and then you'll smell the ammonia or cologne or whatever, no matter where you are in the lecture hall. But it won't be quite as strong because the molecules of the ammonia or whatever have sort of dispersed throughout the air. And likewise, we're sort of, in other words, you're sort of more likely to get collisions with these molecules when they're all bunched up in one place, and you're likely to encounter more of them. If they're spread out evenly across the room, you're likely to encounter a few of them no matter where you walk. And so that would be, as someone spills ammonia in a chemical lab or something, it's really strong for a while until it sort of permeates through the lab. So the idea here would be that we're better off having an even distribution. This is about as bad as you can get with a horrible distribution, everything concentrated in one cell. We're better off instead having an even distribution where we say that given for example, consider dice rolls, and I can say that, given a dice roll, if I happen to roll a dice 6 times, yes, I might get one of each number. I might get 2 1s and 2 2s and a 4 and a 5 and no 3s and no 6. When we talk about the idea of probability, we're talking about the law of large numbers. So we say if I roll the dice 6 million times, I would expect to get about 1,000,000 1s, about 1,000,000 2s, about 1,000,000 3s, and so on. I don't expect to have hugely skewed values, but if I just roll the dice 6 times, I'm not necessarily going to hit, 1, 2, 3, 4, 5, and 6. And you can roll the dice yourself to see that. You're not roll it 6 times, you're not going to get one of each number necessarily. Same thing here. When we say the keys are going to be evenly distributed among, or the results will be evenly distributed, not D, get rid of that letter, there we go. The function is going to evenly distribute our keys among the indices 0 through 6. What we're saying is, I have, say, an infinite number of keys. About 1 over 7 of them would hash to 0, and 1 over 7 of them would hash to 1. 1 over 7 of them would hash to 2. Let me actually change this to n minus 1. So however large our table is, we expect 1/nth of them to hash to one cell, 1/nth to the next cell, 1/nth to the next cell, and so on. So just like I can say, given a random dice roll, there's a 1 in 6 chance it ends up at each of the numbers. Likewise, I say, given a random key, there's a 1 over n chance it ends up at each of the n table cells. And so that's what we want here. There's a 1 in n, if you pick some random key and hash it to an index, and then pick some other random key and hash that to an index, and repeat that experiment over and over and over again, what we want is that about 1n of those keys we pick are going to hash to 0, about 1n of them are going to hash to 1, 1 over n will hash to 2, 1 over n will hash to 3, and so on and so forth. That's a good hash function, one that evenly distributes your key set among the possible indices. And so then, as we said, just as you might roll a dice 6 times exactly and not get exactly 1 1, 1 2, 1 3, 1 4, 1 5, and 1 6, likewise, I can then pick n strings, and I'm not necessarily going to get one of each index. I could easily pick 3 strings and have 2 of them hashed to 0, just like I might easily roll a dice 3 times and I might get 2 1s in those first 3 rolls. Probabilities are more dealing with large numbers, so we're sort of saying over the course of all the keys, we expect that we have an even distribution. And now we're randomly picking keys from that set. We expect those keys then to be as nicely distributed over the indices as possible, but certainly, there's no guarantee we're going to get exactly one of each index. Just like when I roll the dice 6 times, there's no guarantee I'm going to get one of each number. We're talking about more the overall large performance, and then the particular keys we pick for one trial, one set of 6 rolls of the dice, or one selection of n keys, may or may not fit that pattern exactly, which is why we get collisions. Like I said, if you pick 365 random people, you're not likely to get 365 different birthdays, even though it could happen in theory. And yet, we would expect that over the large population, about 1 over 365th, 1/365th of the population was born on each day. But that doesn't mean that if you pick 365 people at random, you're going to get 365 different birthdays. Okay, that's what makes a good hash function, an even distribution of the possible keys among 0 to n minus 1. So what we're going to look at is a very easy hash function for integers in the context of the first kind of hashing we'll look at, which is known as open hashing. It's also called separate chaining for reasons which will become clear very shortly. And the hash function we're going to use will take a key in the set of all integers and hash it to a table of size 7. And the modulus function is what we use. The modulus function is a beautiful hash function, at least it's a nice simple one for our purposes, because what it does is consider all the integers, you have a nice even pattern of every 7th integer hashes to 0 mod 7, the ones that are multiples of 7. The ones that are 1 larger than that all hash to 1 mod 7. The ones that are 2 larger than that all hash to 2 mod 7. The ones that are 3 mod larger than that, than multiples of 7 all hash to 3 mod 7, and so on. Basically, 1/7 of the integers are multiples of 7. 1/7 of the integers are multiples of 7 with a remainder of 1. 1/7 of the integers are 2, larger than a multiple of 7, and so on and so forth. So a hash function, this hash function does exactly what we want. It takes the set of all integers and evenly distributes them. So that 1/7 will hash to 0, 1/7 will hash to 1, 1/7 to 2, 1/7 to 3, 1/7 to 4, 1/7 to 5, and 1/7 to 6 mod 7. So this is exactly the kind of hash function we want. It'll evenly distribute the integers among the possible keys. Now that means if we pick 7 integers at random, those 7 integers might hash to the values 0 through 6, or we might get a collision. But the idea is over the long run, we expect that at least the hash function is going to give us, over the long run, an equal chance at each key. And so then the only factors we need to deal with are, the kind of random factors we get when we actually pick our particular keys. So we're not going to spend too much time discussing the mechanics of hash functions. In fact, we've probably spent all the time we're going to spend right now discussing it. I just wanted to give you a feel for what the important property is of a hash function. There's a whole science behind hash functions we're not going to get into in this class. I'm more concerned about you understanding the data structure itself. And we say, assuming we have a good hash function, how do we proceed with our data structure? The manipulations, the insertion, the removal, that kind of thing. So that's kind of what we're focusing on at this point. And we're not going to ask really anything more about the hash function other than know it should evenly distribute the keys among the index values. So that said, what happens if we insert 16 into this table? When we're dealing with open hashing, what we're going to do is build a linked list off the individual indices. So if I try to insert 16, well, 16 hashes to 2. I could add a node at this place that would hash to 2. And probably, I'd have initially in the table, I'd have all null pointers. And I could say, well, I want to insert 11. 11 hashes to 4. And so I'd start a linked list, forget about this null, and I'd start a linked list containing the number 11. And then let's say I hash 9. 9 also hashes to 2. There's a collision. 16 is already there. So what we do is we add 9 to the linked list already being built at cell 2. That is, the way we resolve collisions is we don't really try and resolve them in any way. We simply say everything that hashes to 2 is in one large linked list at cell 2. So whether we have one thing hashing to 2 or 20 things hashing to cell 2, doesn't matter. We just have that just determines the size of our linked list. And so likewise, I can hash 13 in here, and 13 hashes to 6. So 13 would go there, and so that null wouldn't be there anymore. And then I can also insert 30. And 30 hashes to 2, so I'd add one more node in the linked list. One thing you'll notice is that I'm going to tend to pick really bad data sets. If I pick 5 elements at random, chances are we're not going to have 3 of them hashed to 2 in a 7-element table. But it's certainly a possibility, and the whole goal of our discussions here is to show how collisions get handled, which means I need to sort of talk about the worst case. If the only thing I ever give you is the nice case, where you have no, if the only thing I ever give you is the nice case where you have no collisions, you're not going to see how to resolve collisions. And so as a result, it's sort of important for me to show you the worst case, come up with the worst possible data sets, and show you how extreme situations would be handled. And then you can do that to a lesser extent when you only have a few collisions, and you don't do it at all when you don't have any collisions. And so that's going to be my goal here. So keep in mind as we discuss open and closed hashing both, that the kind of data sets I'll be using as examples are not things we're going to tend to run into in real life, precisely because our hash function we expect to be good, and so we don't expect that the particular set of data we generate is going to be one that hashes a bunch of stuff to the same location continually. That said, in our example here, we have 3 things hashing to 2 out of our 5 elements. Now, if we're going to talk about insert here, we can say insert can be thought of as constant time. Yes, we said, well, you have to traverse to the end of the list to dump 9 at the end. You have to traverse to the end of the list to dump 30 at the end. I could have inserted 9 before 16 and then 30 before them both. In other words, I could have done insertion at the start of a list. I did it at the end of the list because I don't really have the ability, once I've written on paper, to suddenly move that node over, like I would if I was drawing on a whiteboard. Also, I could have had a sort of a makeshift tail pointer on the end of these lists, and so that way that makes it easy to append to the end as well. So using either of those two ways, having a tail pointer or appending to the beginning of the list instead of the end of the list, both those ways, insert would be constant time, even though it may have not looked like it would be constant time the way I did it here, because I'm adding to the end. I was adding to the end of the list with no tail pointer. So as a result, we could get insert to work in constant time. However, to do a find is going to be dependent on the length of the list. Because if I want to find 30 now that I've inserted in the table, I hash on 30, I get 2, and what I need to do then is search down the list and find 30. And in fact, it would be even worse if I did an unsuccessful search. If I want to look up 37, I'd hash on 37, that hashes to 2, and I'd search down this list until I reach the null pointer, learn that I have never seen 37 in this list, and then proceed to go ahead and return that I didn't find the value 37. So as a result, a find is going to be dependent on the size of that list. And likewise, if I want to remove a value, I'll have to traverse down the list again to find the value. And then once I find it, I can remove it. So once I have the pointer to my value, I can get rid of it in constant time. But traversing down the list to find it is going to be linear, or it's going to be based on the length of the list. And so with find and remove being based on the length of the list, it would seem that what we've got here is, as I add more and more and more values into this table, these list sizes would seem to be about n over 7. Where if I insert n elements into the table, about 1/7 of them would end up at each cell, so these list sizes would be about n over 7. And order n over 7 is equivalent to order n. It's linear either way. We're just saying, okay, now we have a constant of 1/7 in front of it. The point being that the running time for find and remove would grow proportionately to the growth of this length of the list. So I can say, and as the data set size grows, the list sizes grow proportionally, and find and remove grow proportionally to the list size. So we could say under this idea, even though insert would be constant, it could take us, in theory, linear time to find a value because we'd have 1/7 n nodes in our list. And likewise, to remove a value could be linear time because we'd have 1/7 n over 7 nodes in our list that we have to search. And so that doesn't really give us a great speed advantage. We'd almost be better off with an AVL tree or something like that at least gave us log n performance for find and remove. However, we're not stuck with this idea. We have the concept here of a load factor. Before I remove this slide, note we have separate chaining. The name is separate. The alternative name is separate chaining because we're building separate chains off the table cells. Open hashing is called so because we're not inserting the values into the table. We're building linked lists instead, so it's a more open kind of structure instead of being confined to just the table itself. Separate chaining is so called because we're building separate chains of nodes. So that's why those two names are for this table. So we have the definition of a load factor, which we can say is equal to the number of elements divided by number of cells in table. Essentially, it's a percent used. Percent used metric. We're trying to ask how much of the table is being used, and what this is, we're basically saying n over size. And in this case, your load factor can be greater than 1 for open hashing. As the table have more than 7 values in it. I could have 2 nodes here, and a node here, and 3 nodes here, and a node there, and 2 nodes here, and a node there, and 2 nodes here. That's a possibility, and certainly there's more than 7 nodes in that table, even though I only have 7 cells. So the open hashing allows me to have a load factor that's LF greater than 1. Or closed hashing, we're going to only write things into the table, and so our load factor there is going to have to be 1 or less. what we can do is either bound the list length, or 2, bound the load factor. If we bound the list length, we might say, for example, as soon as one of these lists would be size 4 with our next insertion, we will do something about it. Or if we bound the load factor, we'd say as soon as the load factor exceeds 4, which would mean as soon as we expect the expected list to exceed 4 in length, or to be 4 in length. Or, so let me say, I'm sorry, the load factor would be 3. Let me start again. If we're going to bound our list length to be 3 or less, then we'd have to fix something as soon as the first list exceeded 3 in size. If we're going to bound our load factor to be 3 or less, then we will do something when the expected list exceeds 3 in size. In other words, if the load factor is 3, what we could have is every single list in table cells 0 through 6 could be size 3. That is, we could insert 21 elements and get every list being of size 3, and then inserting element 22 would force one of those lists to be size 4. In reality, if I had 21 elements in the table, I may have had some of these lists be size 2, and a few more would be size 4 already. Just like here, I can say I have 3, 4, 5, 6, 9, 10. I have 12 elements here. Let me add in 2 more and say, oh, I've got 13 now and 14. So I say now I've got 14 elements in that table, and yet that doesn't mean every list has length 2. I have 14 elements, 7 table cells, but some of the lists are only length 1 because some of them are length 3. So, but the expected length of a list is 2 because we have 14 elements and 7 cells, and we expect a roughly equal distribution. So that would be the idea of bounding the load factor. Bounding the list length would say as soon as one of these lists becomes too large, we'll do something about it. Bounding the load factor says one of the lists might become a little larger than we'd like. We're talking about the expected list length. And as soon as the expected list length becomes too large, then we'll fix something with the table. And that just means now, okay, one of the lists might have gotten a bit larger. This list could be size 4 as long as some of the other lists were size 2 or 1. So it's a matter of whether we're going to try and fix the problem as soon as the first list increases to size 4 or as soon as the expected list increases to size 4, which would be, in this case, 22, the 22nd element. So anyway, the question is, what do we do about that? And the answer is, what we will do is increase the table size. We'll talk about some of the mechanics of doing that near the end of the hashing discussions. But the idea will be that if I was to increase the table size, I would have more room for these. If I have these crammed into 7 array cells and then I increase the table size, I'll have more room for these cells in a larger table. The lists are likely to be smaller. And so in that situation, I'd be okay. I'd have to have a new hash function, which is why often what we will do for our hash function is we'll say that h of x equals x mod the table size. That way, when the table size increases, the hash function will increase very nicely along with it by simply saying, well, now it's not, the size is new, so the hash function's new. But the idea here will be that what hashing will rely on, both open and closed hashing, and even extendable hashing to some extent, as we'll see later on, is when things get too crammed in the existing table and it starts to degrade performance, what you will do is make the table larger. You're trading off memory for speed. To ensure a nice speed, you're going to make the table larger. And so by making the table larger, the elements can be scattered over more of the table, and so you're less likely to have collisions, and the list would be smaller. So when we say here the performance we expect for open hashing, on the average case then, we expect those lists to be constant. We'll have some bound of 3 on either a particular list or the expected list. And so the expectation is that even insert and or even remove and find would now be constant time in the average case as well, because we expect those list lengths to be constant time. And so as a result, or we expect them to be constant time because if those list lengths are bounded, if we know the list lengths are always going to be 3 or less, then, and typically it's the load factor we would worry about. We wouldn't worry about a particular length of the list, but more just the load factor. So the expected list length would be 3 or less. That means the expected list length is effectively constant all the time, no matter how many values we've inserted into the table. And so the expected time to traverse that constant size list is 1. And in the worst case, we have very odd data sets and everything hashes to the same place, or the load factor tells us the expected length of the list, but in reality, I could have all 21 elements. If my load factor is 3 and the table size is 7, that means I can fit 21 elements in the table before having to do a rehash. I expect that I'll have 3 elements at each cell. In reality, I could have 21 elements all at cell 2. So my worst case is going to be very unlikely, but I can have order n for all 3. So it's one of those situations, much like the skip list, where we say we're not really going to hit this worst case too often, but it's there as a possibility. So if you needed an absolute guarantee that you wouldn't hit order n, then you'd have something comfortable like an array, which has a definite worst case of logarithmic time. But skip lists and hashing, they say, yeah, the worst case is linear time rather than logarithmic time like an AVL tree, but it's unlikely that we'll hit that worst case. So we're often okay accepting the average case because we don't expect that worst case to occur. So that's open hashing. Closed hashing will end up having the same results. That insert, remove, and find will be constant time and in the average, and linear in the worst case. So that's going to be the performance for both open hashing and closed hashing. So the question is, what will be the difference between them? And we haven't talked about closed hashing yet, but what will be the difference? Open hashing, as we've already said, has a load factor, or can have a load factor greater than 1. So in a limited table size, we're able to fit more values and still get the same performance. Where for closed hashing, we're going to be writing values directly in the table. If I want 21 elements, I'm not going to be able to fit them in a 7-cell table. With open hashing, I can fit 21 elements in a 7-cell table and still have pretty decent performance. So we'll be able to have a load factor greater than 1 for open hashing. On the downside, we have, so that's sort of an advantage if it's important to us. On the downside, we have, and this is one reason open hashing sometimes doesn't get used, we have dynamic allocation for insert. For remove as well, but as we'll see, removes are sort of handled in an irritating way, and in closed hashing as well. But dynamic allocation for insert, whenever I want to insert a node into the table, I have dynamic allocation to worry about to create a new node. And that's important because, as we talked about way back when with lists, the linked versus array implementations of certain things, that can be a subtle trade-off when dealing with structure comparison. We said that if I'm going to use a linked or a contiguous implementation to implement, for example, a stack, well, we might have the idea of, we said one of the downsides to the linked implementation was we do have the contiguous, or we do have the dynamic allocation and removal of the nodes, where the array with the array, everything was already there. And that wasn't a big difference, but it was a slight time hit. That dynamic memory allocation and deallocation was constant time, but a slightly higher constant than we'd like. And so therefore there is a bit of a time hit if we're doing frequent dynamic allocations. And the places where hash tables would be used would be things where insertion and lookup are vitally important to be done quickly. And an example of that would be the idea of a symbol table in a compiler, where you say the compiler is looking over your variables, and it says, well, I've got these variables that I want to be able to hash into a table. Or I have these variables, and I want to know where the memory locations are, so that as the compiler traverses down the rest of the code, it knows what memory location to replace a variable with, or whatever, and it wants to know information about the variable, what type it is, and so on and so forth. You'd have a symbol table, where you say the key into your symbol table is your variable, and then the record attached with that key is some information about that variable. Just like you say, you look up your social security number in the university database, and the record I get back contains the social security number and a bunch of other information about you. Likewise, I can say you look up the variable name in the symbol database, and what you get back is a bunch of information about that variable. And the compiler, as you might imagine, would need to do those kind of things frequently. in order to do type checking and make sure a code line you've written is legal, it needs to know the types of the variables involved, so it needs to look the variables up to get the types, and it needs to know the memory locations of the variables so it can write the assembly code. And so being able to insert and look up very quickly a variable name would be of vital importance in a compiler. And so this is one area where that might be used. You can use hash tables to implement compiler symbol tables if you want. And so in that case, even that dynamic allocation might be more of a time hit than we want because it would slow compilation down, which is where the closed hashing would have some appeal. The closed hashing would say, for a given number of symbols, we'll need a larger table, or we could need a larger table, but we would save the dynamic allocation time. We wouldn't have to be doing those dynamic allocation nodes each time, so we'd be a little bit better off there. So that will be the open hashing, closed hashing trade-off. Now in dealing specifically with closed hashing is also known as open addressing. The reason being, it's called closed hashing because we'll be writing directly into the table. It's called open addressing because where we put a value is not necessarily going to be where we expected to put it. So if I say now, things will start off in a similar manner. Here's my table. 0, 1, 2, 3, 4, 5, and 6. If I want to say I'm going to, well, once again, h of x equals x mod the table size, which in this case is 7. Now I'll say 16 hashes to 2. We write 16 into the table. And I say insert 11, and 11 hashes to 4. We write 11 into the table. So that's not too different from last time. Now I say I want to insert 9. 9 hashes to 2, but 16 is already there. And unlike with open hashing, we don't have a linked list just to dump 9 into. And yet we want to put 9 in this table. We don't want to say, well, too bad for 9. That's not going to work. Forget 9. Similar to if I'm trying to put a new variable name into a symbol table for the compiler, you don't want the compiler to return an error message to you saying, oh, well, I know you want to use the variable name x, but unfortunately that has a collision with something else, the variable num exams that you used earlier. So you have to change your variable name. You should be able to use whatever variable names you want. So we do want to put 9 into this table. And since it can't go at h of 2, or it can't go at 2 where we've hashed it to, it has to go somewhere else. And the question is, how do we pick that somewhere else? Because we can't put it at 2 where the hash function tells us to put it. And one strategy is, oh, we'll just pick some random other cell then. Pick, oh, heck, 6, and dump 9 there. Certainly it works. I could stick 9 at 6. There's nothing there right now. The problem with just picking a cell out of the blue is that if we just pick a cell out of the blue at random and stick 9 there, finding it later on is going to be difficult. The nice thing about a hash function was that if we keep passing the same input in, we keep getting the same output. Every time I send Sue into the hash function, I'll get 3. Same input, same output. Every time I send Jim into the hash function, I get 5. And likewise with the integers, every time I send 16 into x mod 7, I get 2. Every time I send 9 into x mod 7, I get 2. Which means the whole point was I insert it based on the index I get the first time. I look up based on that index the next time. So when I want to find 11, I say, well, run 11 to the hash function. I'll get the same index I got before, namely 4. I can look at 4. That's where 11 is. That was the power of this whole idea, was that the function, otherwise I could just dump it anywhere to begin with. I use a function because if I have a function tell me where to put it, that same function can tell me where to find it later on. As opposed to just dumping 16 wherever I please from the start, then it's going to be harder to find later on, require a larger search. I use a function so that if I put it where the function tells me, I can then find it in that same place later on. The function will tell me where to find it. So saying 9 collides at 2, oh well, stick 9 wherever else, isn't an appealing option because that wherever else is not going to be something we can find later on. So what we want is 9 has to go somewhere else, certainly. This has to be determined by formula. That is, we can't just pick a random location for 9. We have to, through some mathematical formula, determine where 9 goes next. We need some ordered sequence of cells, some sort of whatever it is, a formula of some kind that gives us a sequence of cells to try. That says, oh, if 9 doesn't go in 2, then the next spot you should try is 5. Example. And so what we then do is we say, well, if 9 collides at 2, we will go ahead and put 9 at cell 5. Because the function says, if 2 collides, then try 5 next. Then when I go to look for 9, I'll say, well, 9 collides at 2. So, I'm sorry, I look at 2, cell 2. Now, the first thing would say 9 hashes to 2. But 16 is there, not 9. So I tell myself, well, if I had inserted 9 into the table, it's not at cell 2, might I have tried my second alternative location? And I could then look at 5, which would be the formula-defined alternative location, and I'd find 9 there. And that's the idea. If I have a formula that says, if there's a collision at 2, try 5, then when I go to look up 9, I can say, well, 9 wasn't at cell 2, I should try cell 5. In the same way that I say the hash function tells me where to put the value, and therefore it tells me where to look for it later on. Likewise, if I have a more general kind of function that says, here's the sequence of cells to try in order, then I can try that same sequence in that same order when looking for my value. So it's just extending the idea. Instead of saying, here's one cell in which to put your value, and then one cell in which to check your value, we recognize we might have collisions, so we say, here's a sequence of cells with which to try inserting your value, and then follow that same sequence when looking for it. But that's the key idea here. If we determine where 9 goes by formula, if we have some sequence that we can generate to determine where to try to put 9 into, then we'll put 9 into the first empty cell we get. And then we'll follow that exact same sequence when looking for 9. Which will mean that however many times we had collisions before finally finding an empty cell for 9, we will have that many unsuccessful lookups in the table before finally finding 9 later on. So we'll come back to a concrete example of this in a moment. First, I want to sort of introduce the general idea. So this is known as probing, where we say a probe is a lookup into the table. And so we'll use I to be equal to the number of probes so far, and I will start at 0, because initially we won't have done any probes so far. And we will say now, this will sort of be our overall function. Given a value and the number of probes so far, the way we will determine where this value goes is by saying we have our hash function. That gives us the initial location, plus f of I, which will be called a probing function, and then the whole thing modulus the table size. We do modulus the table size so it'll wrap around. If the sum of these two things gives us 11, for example, well, that's really cell 4. 11 mod 7 is 4, and so it wraps around and brings us to cell 4. So whenever we do any sort of calculations in the hash table, before we do anything when we're done, we'll do a whole thing mod size. And that makes sure that if we've run off the end of the table, we'll wrap around to the beginning again. And that's effectively what modulus does for us. So this is our general formula for looking up in a closed hashing table. The initial location is given to us by our hash function. But we will try then, we will add offsets to that initial location using the probing function. And the probing function, most commonly, firstly, for every probing function, we're going to have that f of 0 equals 0. So in other words, the initial location will be the first thing we try, because the first thing we'll say is, well, if I've gotten 0 probes so far, the first time I try to insert my value into the table, When I first try to insert 9 into the table, for example, I haven't done any probes yet. I haven't done any lookup for 9, so we'd look up h of x comma 0. And I'll write this on the next slide in a moment. So I try my initial location plus 0. If my probing function starts at 0, then the first cell I will try will be my initial location, because I'll have initial location plus f of 0, and that will be the initial location plus 0, and that will be the initial location. After that, I will be adding increasing offsets to my initial location to give me different cells. And so by making that probing function different, we get different offsets. And one possibility we have here is that of what is known as linear probing, where we say that f of I equals I. The simplest possible linear function. What this means for us is we are saying more generally here that h of x comma I is going to equal h of x plus I at size. Or in other words, what I'm saying here, in general, I would be saying, the general rule would be I would try h of, this would be the first cell I try when inserting something, and that would equal h of x plus f of 0 mod size. And then I try, if that's a collision, I would then try, I'd say, well, now I've done one probe so far, so this would be my second probe. And I say then I would try this cell, h of x plus f of 1 mod size, and if that's a collision, I would then try, I'd say now try this function again, but now I've done two unsuccessful probes, and so I say h of x plus f of 2 mod size, and so on and so forth. For linear probing, what this is going to mean is I will be trying h of x plus 0, h of x plus 1, h of x plus 2, h of x plus 3, and so on. All these always mod size. H of x plus 4, and so on. So linear probing would be our example. Our general rule will be this. We'll try the initial location plus f of 0, the initial location plus f of 1. If that's a collision as well, the initial location plus f of 2. If that's a collision as well, then the initial location plus f of 3. If that's a collision as well, then the initial location plus f of 4. And we'll keep trying f of 5, f of 6, f of 7, keep, tossing larger and larger I values into that probing function until we finally hit a cell that has no collision. Or, if the table is full, then we wouldn't be able to do any insert at all. But what we have here then is, for linear probing specifically, when the probing function f of I is just I, then this is what we're doing, h of x plus 0. If that's a collision, as it was for 9, then we try h of x plus 1. And if that was a collision, then we get h of x plus 2. If that was a collision, we try h of x plus 3, and so on. So by way of an example, let's draw the table one last time. 1, 2, 3, 4, 5, and 6. And so what we have here now is 16, I can hash into 2. 11, I can hash to 4. When I want to insert 9, I try 9 plus 0, and that's a collision. So I try now 9 plus 1, 2 plus 0, and that's a collision, so I try 2 plus 1, that's 3, and 9 can go there. Now if I insert 30, I can say, well, 30 also hashes to 2. I try 2 plus 0, that doesn't work. I try 2 plus 1, there's a collision with 9. I try 2 plus 2, there's a collision with 4. I try 2 plus 3, that's opened. I can look up 30 there. I'll put 30 there. Later on, when I go to look up 9, I'll say, try 2 plus 0, that didn't work. Try 2 plus 1, hey, there's 9. If I try to look up 30, I say, try 2 plus 0, well, that's 16. Try 2 plus 1, well, that's 9. 2 plus 2, 2 plus 3, there's 30 at cell 5. And of course, like I said, since you're really taking everything modulus the table size, I would try here, if I wanted to search further, I would try 2 plus 4, which is 6, and then 2 plus 5, which will be equivalent to cell 0, because 7 mod 7 is 0. So we will wrap around from the bottom to the top of the table. That's what the modulus function will do for us. So if I'm looking for 37, which also hashes to 2, I'm going to say, well, 37 is not at cell 2, it's not at cell 3, it's not at cell 4, it's not at cell 5, and then we look at cell 6 and it's empty. And that tells us we can stop for the moment. We're going to ignore the idea of removals for the moment. We'll talk about that at the beginning of the next lecture. If we have no removals in our table, then if there are no removals, the problem we are faced with then is to say, when do we stop searching? We can stop searching as soon as we hit an empty space. If I'm looking for 37, either I would have started searching for 37 at cell 2 and followed the appropriate probing sequence. Either I would have hit 37 by looking at the probing sequence values already, or I would have put it, now this is the next cell in the probing sequence. I've tried 2 plus 0, 2 plus 1, 2 plus 2, and 2 plus 3. I'm now trying cell 2 plus 4. I haven't hit 37 at any of the previous values in the probing sequence, which is what this is called. I didn't write that before. You had a probing function. This is a probing sequence. I may as well go back and write that. So just so you have it written down, the sequence of cells to check we get then from the h of x plus 0 to h of x plus 1, h of x plus 2, whatever, that's known as a probing sequence, the sequence of cells we check. And so for 37, our probing sequence was exactly that, 2, 3, 4, 5, 6, 0, 1. And I tried 2, 3, 4, and 5. Those were the first 4 values in the probing sequence. Those were collisions. So then I try cell 6, and that's empty, and I know that I can stop looking for 37, because 37 either would have been in one of those previous 4 cells, or 37 would have been here, or if 37 was later in the sequence, at cell 0 or 1, something else would have been at cell 6. If we haven't done any removals yet, then we know cell 6 would not be, we would not have skipped over cell 6. The sequence for trying to insert 37 was 2, 3, 4, 5, 6, 0, 1. Since cell 6 is empty, if we had inserted 37, if we had had collisions with all 4 of those, we would have put it at 6. Or something else like 13, which actually hashes to 6, would have been at 6, and we would have put 37 later in the table. But if there's nothing at cell 6, then there's no reason to believe 37 is anywhere in the table, because 37 would either be at cell 6, or it would have been later in the sequence because something else was already at cell 6. In no case would we have said to insert 37, try 2, try 3, try 4, try 5, leap over 6, and go to 0. So when doing an insert, I'll simply traverse the probing sequence until I find an empty cell. When doing a lookup, I traverse the probing sequence until I find an empty cell. And if the value is in the table, I will find the value in the table before I find an empty cell. If the value is not in the table, I will hit an empty cell. But once I hit that empty cell, I can stop looking. There's no reason for me to check 0 or 1. There's no way 37 could have been there. Because if 37 had been at cell 0 or at cell 1, it would have only gone there if something else had already been in cell 6, so that 37 couldn't be inserted in cell 6. We wouldn't have skipped over cell 6. We would have tried to put 37 at cell 6. And the only way we would have not done that would have been if something else had already been at cell 6. Since the cell's empty, nothing else is there, clearly. And so there would have been no reason to skip over cell 6. So we can safely say at this point, since we've hit an empty cell, that 37 is not in the table. And so outside of removes, those are the two ways we handle things in the closed hashing table. We have our probing sequence determined by the initial location. The hash function gives us the initial location. The probing function gives us the offsets. And so as we've seen before, the initial location plus the probing function value gives us our sequence, which in the case of things that hash to 2 with linear probing is going to be 2, 3, 4, 5, 6, 0, 1 on this table. And so we follow that probing sequence, trying each index in succession until we find an empty cell and put the value there. That's insert. If the table happens to be full, we won't find a value, and when we've done, the number of probes equal to the size of the table, we would stop. If what we're trying to do is to look up in the table, we will again follow the same probing sequence. As long as we don't find the value, we keep checking the next value in the sequence until we hit an empty cell. So I will check cells 2, cell 3, cell 4, and cell 5 when looking for 37. When I check cell 6 and 6 is empty, then I know I can stop looking for 37. And so that's the idea behind closed hashing. We have a few more details we need to cover in the next lecture. We're going to stop here for now. This will be the idea then. For insert, follow the sequence until you find an empty cell, put the value there. For lookups, follow the sequence until you either find your value, which is a positive, or you find an empty cell, which is an unsuccessful search. What we'll start talking about next time is how to deal with removes in this whole idea, and also look at a few different probing strategies other than linear probing. That's it for now. Talk to you next time. See ya.